I am also very glad to see, just one sentence, I must tell that my inspiration and my starting, the initiation to research, somebody can question being an electrical engineer, come to me, and it can come to many. The main initiation and inspiration, I am very glad that he is here today. That several years ago, that time very young, so he was the inspiration. He started, he came to me that he has been guided on nuclear reactor control. I told, I don't know nuclear reactor anything. How can I guide? So he retired as an associate director of BRC, and then now he is a visiting professor in one of the IITs. So that is the starting point. After that, of course, many students have done PhD on this topic. But we have a lot of small reactors, which is of capacity 200 megawatt, 220 or one in that range. And then the government of India thought that that kind of reactor is not sufficient to gather the power required. And it was thought that the large reactor has to be built in so that the large power can be obtained. And the large reactor, what happens, the control system for the small reactor is much easier. It can be modeled as an order differential equation in the reactor, and it can be controlled by classical control, PID control or Indo-French kind. But the large reactor, I am coming to much on that it is not very easy to control, design the control system. Whole modeling is itself is a very big task, very big challenge. And it has taken several years' time to get the model of this. So I will be discussing why the large reactor. So in one of the plans in the government of India, maybe 9th plan or 10th plan, it was thought that the large nuclear reactor has to be built so that the large electrical power can be on. And that is the starting point. And then the research started how to design such a reactor, how to mathematically, how to model that reactor, and how to control, how to design the control system, and how that control system can be implemented on a test-bed reactor, which has been done also at the DRC. And then I discuss some of the control techniques, how does control engineer come to control such reactor, and some of the control techniques. And there are certain issues in controlling such reactor that I will be discussing, and then certain simulation results of this large reactor, the nonlinear simulation, which we are discussing, and certainly some of the publications and other things. So in this order, I will take that. I contact them to stop. That is the introduction, then the control problem, mathematical model of the reactor, nonlinear model, linearized model, the standard state space model. How this nuclear reactor is modeled in state space in several order state space model. Then SMC, sliding mode control. Of course, this is a scheme on sliding mode control. So how the sliding mode control has been designed for this reactor, and what are the existing techniques on sliding mode. As my earlier speaker talked on discrete time sliding mode, here also I will show how the discrete time sliding mode control has been designed. And chatter-free control approach. In the discrete time system, those who are working on discrete time sliding mode control, there are two schools of thought. One is the signum function using, which is the direct discretization of the Reactor law for continuous time system. There you get a chattering. In theory also you get a chattering. I mean, it cannot slide. It slides above the sliding surface. If you root from the continuous system, and then if you design a discrete time sliding mode control, then it has been shown that it no longer can slide exactly, as opposed to continuous time sliding mode control, where if there is a matched uncertainty, then it can be known, or it is known very much, that it exactly slides, the fleet of solution, which is not possible if there is a signum function in the discrete time, in the control. So there is a approach side by side. Then there was a discussion in 2004, I think, in Barcelona, that discrete time system which doesn't have that kind of sliding, then it is not a sliding mode. Then it was termed as, it is not a sliding mode, it is a quasi-sliding, because it is not exactly sliding in theory also. Then of course the Woodkey has proposed that without switching there can be a discrete time slide. There is no switching, and then it can exactly slide by his infinite algorithm. So without disturbance in discrete time system, that is which I am going to show here certain development has been done. That means there is no signum function in control. If you just apply the equivalent control, then in discrete time system, it can slide exactly without any stuff. So that can be considered. That kind of work is done by Dr. Levy, by the Woodfield, by the Dr. Lewis. So several people have shown without switching that can be possible a sliding mode in discrete time. I am talking the category component. Then some applications and the simulation results and uploaded. So this is the nuclear reactor coming first part, large part of the talk. What is nuclear reactor? A nuclear reactor is a device in which control fission chain reaction takes place. It is the fission, we know that in 1944, due to the Otto Hahn, a chemistry professor in Germany, in Marburg University, it is Otto Hahn. Due to him, he got the Nobel Award for this invention. It is fission reaction. So it is the fission due to which we are getting all nuclear power plants. If the fission is not known, so you cannot, it was not known the power, electrical power can be generated from the nuclear. So it is the fission, the Otto. So that fission reaction, the control problem in a nuclear reactor, it is the fission reaction which has to be controlled. A device, the control fission chain reaction. I will come to the point, what is fission reaction. So it is the fission reaction that has to be controlled, and that is done by a control system. The fission reaction has to be controlled. The reaction, if it is controlled, then the reactivity will be controlled, then the flux will be controlled, then the power will be controlled. So that is the idea of a nuclear reactor. Typically, in a nuclear reactor, neutrons are absorbed in the fuel, uranium-235, which undergoes fission, resulting into the production of fission fragments. Neutrons and other radiation and release 200 mega electric volt energy per fission. This much energy is released 200 MeV per fission. This much energy is released per fission. Now, this is the structure, that is the core part, and then of entire mechanism, and this is the nucleus neutron collision that hitting, and then the nucleus is split into two parts, and then huge energy is liberated, released, and that energy is kinetic energy in the form initially, and then it is converted to the heat energy, and it is taken out by the coolant, the secondary side, to make that power plant close to the power. So there are several classifications. One is the first reactor, in which the fission reactors are maintained by the first. As I understand, in France, the first reactors were more popular than the thermal. The size can be small, but the safety is very important. So what I understood, that France, the many reactors are operated using the fission reaction that takes place by the first neutron. They are majority of the fission reaction, so they are known as the first reactor. But in India, we have mostly the thermal, in which the fission reactors are maintained by the thermal means. So this is the difference, the thermal reactors and the first reactor. The first leader test reactor is converted on only the first reactor operational. Prototype first reactor is a powered first reactor under commissioning at Calcutta. All other reactors are thermal. So there are other classifications, the light water cooled reactors, the boiling water reactor, pressurized water reactor, then the one which I'll be talking here, the pressurized heavy water reactor. That is what is this kind of reactor, and how the reaction takes place, how the fission takes place, and how the mathematical model is obtained for the fluids that work. There is another reactor is under design, which is advanced heavy water reactor, which is in the design stage and it can be commissioned. Then there is a gas cooled reactor. then the coolant can be gas, then the liquid metal cool reactor, the different classifications of the nuclear reactors are in this slide. Then the core part of the reactor, which consists of the fuel, the nuclear fuel, then the moderator, by which the freshly liberated the neutrons are slowed down. That is called the moderator. There is a coolant by which the heat is taken out from primary side to the secondary side and control rods and element. That is heat by which the reactivity is controlled. But in this reactor, the reactivity is not controlled by the control rod. In this reactor, the reactivity is controlled by the water tube, the jet system, zonal control compartment, where the water level, by controlling the water level, which is connected to a valve, that water level is controlled, and water level controlling controls the reactivity. It absorbs less or more neutron in the reactor, and by which the reactivity is controlled, and reactivity controlling the flux is controlled and the power. But in general, many reactors, the reactivity is controlled by the movement of the control rod. But here, the movement of the control rod is not done. It is the water level. By changing the water level, the reactivity. Then there is a reflector, there is a shield, and neutron flux sensor can be input or extra. Then there is a flux detector. So one has to control one has to measure the flux. So that's why in the nuclear, in the surface, the input flux detector are installed, and from the flux detector, the flux is measured, and which is used for the computer. Then it is, as of December 2023, I mean some statistics, in India, 23 power reactors are operational, producing this many 7.5 gigawatt approximately. Besides 4 research reactors, 2 each at IFCPAR-FUNDED, 1 is IFCPAR for isotope production lines. So around 23 power reactors are in operation. Most of the power reactors in India are the pressurized heavy water reactor of capacity 220 by 4700 megawatt, using 235 uranium as a fuel, heavy water as a moderator and reflector, and also heavy water as a coolant in a separate pressurized high temperature circuit. So this is then the two of them, 540 megawatt, which I will be talking on the modeling and control of such reactor, which are operational at Tarapur in 2006, 2005-6, and 1700 is operational at Takapara since 2011. So these are the reactors, the 540 reactors. The first time in India, such reactor was commissioned, designed, and implemented, and it is producing 540 each. So there are 2 such reactors which were installed in Tarapur in 2005-2006. So mainly my discussions today, I will be concentrating the modeling, control design, and simulation of this such reactor. The PHWR pressurized heavy water reactor of 540 megawatt capacity. 540 megawatt electrical power, so 3 times, approximately 3 times of that is a nuclear power. So these reactors have, now why the control system and modeling is so important? The control system and modeling is so important because if it is a small reactor, then it can be modeled by 2 differential equations. Because the main thing is the flux, the change of the flux due to one reason or other, due to disturbance or heat healing, anything, it uniformly changes. So it can be detected, the flux, and easily the system can be controlled. It doesn't change in a different way in different parts of the reactor. But this particular phenomena, this particular property is not true for a large reactor. Because what happens is the physical dimension, the one which I am talking of, will be talking on 540 megawatt, it has a dimension of 8 meter diameter and 6 meter long. So in such reactor, these things are not true. And that's why its modeling and control system is very complicated and very difficult. So what is that in a large physical dimension reactor, whose length is more than the 25 times of the migration length, which is the slowed down length and the diffusion length, that's for the migration length. Then what happened, this reactor, and what is the problem in this reactor I will be discussing, and what happens, this kind of reactor is from the large reactor. And it required to be operated with flattened flux distribution to produce electricity economically. That is the idea. So what happens in this reactor, if one part, this large reactors, if one part, due to some reason, due to the fault, due to the refueling, due to some other reason, if the flux increases in one part, it is not held in the other part immediately. So that's why that the system cannot be modeled but by one flux equation for the entire reactor. This is the problem. So one has to go to partial differential equation, and one has to model the system by dividing into several zones, and for each zone it can be assumed, it has been assumed, several divisions have been done, and an optimal division has been arrived at that time when it was modeled, mathematical modeling. So what has been done for this large reactor, in one part, in one zone, it is assumed that the whole of the power, precursor, xenon, different things, they are constant over volume, but they vary with specific time. So these variables in a particular zone can be expressed by ordinary differential equation, and they are connected to other zones, neighboring zones, by the neutronic diffusion. So that way the model becomes complicated, and I will show how we have modeled this kind of reactor and how to get a nonlinear model and how to linearize and to get a linear model of very high dimension. So what is happening in a large reactor, as I told, the neutron production and absorption phenomena in one part is not felt in other parts until after an appreciable delay. This coupled with non-uniform rates of production and removal of xenon necessitates the spatial consideration in modeling and control. Reactor needs to be divided into several zones, having its own flux detector and reactivity control device. That means in this case it is divided into 14 zones. Of course it is divided into higher 30 zones, 40 zones, maybe larger zones, but it has been found, it is the model, it is compared, this model is compared with the benchmark model which is given in certain literature, and it has been found the 14 zone division is sufficient to design controller for this reactor, and that mathematical model represents the dynamics of this reactor. However, one can do the further divisions of the reactor by increasing the number of zones. So, and each zone will have one flux detector, and each zone will have one control mechanism. So there are, in this reactor, I will show that it is divided into 14 zones, so 14 input and 14 out. So it is a multi-variable system. So unlike in the small reactor, which is a single input, single output system, it becomes, first of all, the order of the system is very high. I will show that each zone is represented by 5 ordinary differential equations. So 5 into 14, there are 70 ordinary nonlinear differential equations which represent this reactor dynamics. And each zone has an input to the system, and each zone has an output. So there are 14 input, 14 output. So it is a 14 input, 14 output, 70th order multi-variable system. And the control problem is that how to control the zonal power and the global power using this independent control. So this is the control problem for this reactor. So reactor, which is own flux detector and reactivity control device. So this is reactor with one view, the front hub and the back hub. Other views have also their axial views and the top to bottom, the side-to-side views. So this is the front and the back hub. So it has these are the zones, and as I told that its dimension is 8 meter diameter and 6 meter long. So if zone is to be described by a set of equations, and I told the rate of change of power, rate of concentration of the delayed neutron, precursor, xenon, iodine, and the neutron division among the zones is represented by the coupling. The couple neutronic diffusion, they are connected with one zone to another zone, the neighboring zone. Among the various fission products, there is another another very important point to note for the large reactor that various fission products, the xenon enjoyed spatial importance due to its large thermal neutron absorption cross-section and long half-life. The xenon absorbs neutron, and that process is known as the transmutation, and it changes the reactor. So that's why it is very important to model the xenon. And xenon is produced from the iodine after the fission reaction. So that's why iodine has to be also modeled, because its dynamics has to be known, then one can know the dynamics of the xenon. So the xenon, because the xenon absorption of neutron, it can change the reactivity, and if you do not control the xenon and iodine, then the reactor can blow up, that the power cannot be controlled. And that's why the spatial control is. The xenon has to be controlled, not only the power and the precursor, the xenon control, iodine control. So different variables of the reactor are to be controlled, and that is possible by the spatial control or the zonal control system. So major portion of the xenon is formed from the iodine, and only a small fraction results directly from the fission. But the major chunk of the xenon is produced from the iodine. So this is just a fission, the formation of xenon in a reactor, the fission reactor. You can say the cycle, the chain of the fission reaction. How does it happen? The thermal. This is the thermal uranium-235, and 0 time it is produced in tellurium, and then tellurium to less than a minute, the iodine is produced, and then 6.7 hours. It takes the long time. The xenon is produced from the iodine, and then the cesium and rubidium, they are the stable isotope, so they are not considered in the model. They are not important for modeling of this large nuclear reactor because they are very stable isotope. But the mainly is the iodine and the xenon absorbs neutron. That's why the dynamics of the xenon is very important to understand. So and a very less percentage of the xenon, which is directly produced, 0.2% directly from the fission reaction. And majority of the xenon is produced from the decay of the iodine, which takes 6.7 hours. Then what happens? That is not known before some time, and due to not knowing this kind of fact, the proper control of reactor was not done much earlier. So this is what happens with this kind of large size of reactor, and with the xenon dynamics. What actually happens, that I'm trying to explain with you, that increase of the neutron flux, if we consider the reactor in the 2 parts. And the question can come, why one should not be happy the control engineer or nuclear engineer to control the power global? Only the global power can be detected. Maybe there are different tubes, the FCC compartment, but why not at a time? All the tubes can be, either the water level can be controlled, at a time, and one can control the global power. Mathematically one can control, but there is a problem. And that's why independent control of the zonal power is needed, and so that you can control the global power. But why one single controller? There can be several pieces. That is not the question. Question is that why not one global power, global control to control the global? Problem is that the increase of neutron flux in reactor, what happens? Immediately increase the rate of consumption of the xenon. The moment due to some reason in one part of the reactor, if the flux increases, and initially they are all in equilibrium now, and then as the flux increases, neutron increases, then xenon gets a chance to absorb those neutrons. And the moment the xenon absorbs those neutrons, then the xenon gets reduced, and then the neutrons gets chance to further increase. So this goes for several hours. That is, the reproduction to the decay will happen after several hours. So the net immediate effect is that increased rate of consumption of xenon will further increase the neutron flux due to the reduction in absorption of carbon. This process leads to continued decrease in xenon concentration, and a steady increase in neutron flux. So this goes several hours until the xenon is produced from the iodine after 6-7 hours. And then what happens, the reverse process can take place. A xenon concentration starts decreasing. The huge xenon is produced after 6-7 hours. Then initially the few hours, the flux was increasing and the xenon decreased. And the xenon increases, the power decreases, and the reverse process takes place, and xenon concentration starts increasing, leading to reduction of the electron. I am so like this figure, it will clear the thing. So this happens, and if there is a global part, that may be the best explained from here, that whole reactor, if it is divided into 2 parts, it will consider, and if by some reason, if the flux is, this is not working, so what happens, that if the global power is initially they are in equilibrium, that full power, let's say, and due to some reason, so initially if the global power of the reactor is in constant in both the sides, but due to some reason, if the power increases in one side, then what happens, the global controller, it sees the total power increases of the reactor, and immediately the global controller, if there is a global controller, what is the problem? I am trying to explain that if there is an increase, because the total power is measuring, and if there is an increase in the global power, then it applies the control system, which decreases the power, but in both the sides. Because it's not, the global power, it is not taking the power of one part. It is the total power of the reactor. Then what happens, that the dotted line is decreases. So initially it was this, and then due to some reason it increases, and due to the applications of the global control, it decreases here and decreases here. And then what happened, that what I was trying to explain, then that time the one side is the more power, so the xenon absorbs those neutrons, the flux, and then the power increases after, and then the xenon comes after 6-7 hours. Then in one part, one kind of 15 hours oscillation, the power increases and decreases. Other part, it happens in opposite. Then about 25 to 30 hours full cycle, 15 hours half cycle, this kind of oscillation takes place in the nuclear reactor, which is known as the spatial oscillation. And if this is left uncontrolled, then the whole reactor, this oscillation can be unstable and the reactor can blow up, although you are controlling the global. So that's why there is a need for the local power, the zonal power. So this is a fluxing thing. After few minutes it is shown, but in oscillation part cannot be, it is like that. It increases power and decreases xenon, and other part happens in opposite way, so that the global power is lost. But this oscillation takes place in the large reactor. But if it is, this is under only the global control. That's why there is a need for the zonal control or global control, which detects the increase in power in any one part of the reactor, and immediately the control system for that zone it activates, and then it controls the power of that. This is the main theme of this control design of the large reactor. The control problem of the large nuclear reactor: maintain the reactor power close to the set point for power demand, maintain the power distribution close to the desired power, maintain the fractional zonal power close to the respective equilibrium values. The problem has been attended earlier, in the course of this entire study. The output is the control, below the first output, and also the sliding response. So in this talk, I will present the control of these based on the sliding mode. So multiple Newton diffusion equations for detailed accurate representation, Newton production, absorption, leakage phenomena in the nuclear reactor. It's not, practical for control studies. So point kinetic model is very popular, but it's oversimplified, and it is cannot be used for a large reactor. So applied control studies applied for the control studies and analysis for small and medium size. So point kinetic model fails to, as I explained, the spatial effect and the radiation of neutron flux distribution in the core with space coordinate and time. So not applicable to large nuclear reactor. Hence a large reactor, this model is a nodal model, and 540 megawatt PHWR has extensively been studied using the nodal model. The nodal model is derived from the multi-group neutron diffusion equation. Here we have considered two energy groups, the first neutron and the thermal neutron, phi 1 and phi 2. And also it is assumed all the fission neutrons are assumed to appear as first neutron immediately after the fission reaction. Upscattering is ignored here for this model. Then what is done, that these are the two basic equations. The neutron diffusion equations associated with the precursor concentration and expressed as this. The rate of change of, this is the rate of change of, the first neutron is the d of the grad of the divergence of the diffusion is constant into the d grad of phi is del square phi. Laplacian operator, Laplacian equation. This is the leakage flux, the divergence, and the d1 into grad of phi. Minus this is the absorption coefficient, the macroscopic absorption coefficients of phi 1. So at this rate, the neutrons are absorbed. So this is changing the rate of change of first neutron. And then this is the delayed neutron. The beta is the delayed neutron. So this is the prompt neutron. So 1 minus beta is the prompt neutron, and this fraction, and this is the at this rate the fission is taking place due to the phi 1. Some phi 1 is considered, and at this rate the fission is taking place due to phi 2. So net fission neutron, and this is the prompt neutron, and beta is the delayed neutron, and this is the inter-energy macroscopic transfer coefficient. So at this rate the phi 1 is changed to phi 2. And at this rate, the delayed neutron precursor is produced. Idea is that whenever there is a fission reaction, it splits into two species, and they decay again. So that is called the delayed neutron precursor. So they can change the dynamics of the system. So they are to be modeled also. So that is known as the delayed neutron precursor. And immediately after the fission reactions, some neutrons are produced. They are the prompt neutron. So it is assumed that the beta fraction is the delayed neutron, so 1 minus beta fraction is the prompt neutron after everything. Then the thermal neutron, similarly, that this is the rate of change of thermal neutron, and this is the d of the diffusion coefficient, the grad of phi, del square phi, the leakage of the thermal neutron, the absorption, whatever is absorbed due to this this thermal neutron at this rate, the neutron is absorbed, and at this state the phi 1 is changed to phi 2. So this rate is added to the rate of change of the thermal. And similarly, the rate of change of precursor, at this rate the precursor is decreased. The lambda 1 is a time constant. They are mainly divided into 6 groups according to their time constant. So lambda I is the time constant, lambda 1 for group 1, lambda 2 for the group 2, like that. So the precursor, the decay, and this is the prompt neutron, the delayed neutron, beta fraction delayed neutron, which is produced by the fission reaction. So at this state, the delayed neutron precursor are produced, and at this state, the delayed neutron are decayed. So net rate of change of delayed neutron precursor can be considered this time. Then the diffusion coefficient in a spatial variance, in a spatial control, spatial variance, in a large reactor, the diffusion coefficient can be little small, and so that it can be approximated, that the D1 can be taken out of the divergence. So divergence D1 grad phi can be approximated as D1 del square phi, similarly for the D2. Then what is done? The reactor, in this reactor is divided into 14 zones. So for each zone, there are 6 neighboring units. So when what is considered here due to the neutron diffusion from 1, we consider the box H to box K, and this is the equation that d2 dr square, that the flux diffusion from box H to box K is governed by this net rate of change of rate of first neutron diffusion from box H to its neighboring box is the d2 dr square, volume of the box dH. G1 is the diffusion coefficient, and Jr is the current density, and the AHK is the area of interface between box H and box K. So there the diffusion is governed by this equation, and then using the Fick's law, what is happening? The flux gradient, the current density is directly proportional to the flux gradient in space. So J is proportional to the Fick idea, and then this equation is represented by this equation, and then here in this part, this is the point where the partial differential equation is converted into ordinary differential equation by the finite difference technique diagram. Flux of H, the Diff idea, the space gradient, what is approximated as the flux of this minus flux of this in that particular zone, where the flux is considered constant over volume over space. So this minus this by center to center distance, and this is the volume of that box H, area of interface. So this differential equation, the partial differential equation, is converted into ordinary differential equation. This is what is called, what we call that nodalization and nodal technique, that you are converting a large, the whole flux of the reactor by several ordinary differential equations of every zone. Similarly, is done for the first, which is for the first reactor, first flux, thermal flux, and then by Newtonic, the diffusion coefficient from each zone to different zone. If there is a zone, the neighboring zone, there is a diffusion coefficient. There is no diffusion to the non-neighboring. So with all these things, the coefficients are calculated, and then this flux equation of two zones are represented by this. One is the half Newton flux of zone H, another is the thermal Newton flux, which is zone H. So there are two, that zone, if there are 14 zones, then there are 14 first Newton flux ordinary differential equation, and in 14 zones, there are 14 thermal Newton flux equation in ordinary differential. Then what happened? There was a technique which is developed in the Stuttgart, that Stuttgart nuclear research lab, that this can be approximated as 1.5 to 3. Instead of, one can consider, there was a study by considering the first Newton flux and the slow Newton, thermal Newton flux, and there can be 14, 14, 28 zone, but it is not needed. What has been found by different analysis, that it can be to add this flux in this particular way of both equations, and if we consider all the substitution, that VA, sigma A, this thing, then they can be converted, the two group diffusion equation, ordinary diffusion equation for one zone can be converted into 1.5 group, and that flux can be represented by an equivalent flux by H. And what is obtained, this is the values are obtained by this assumption, which is done in that lab. The slow Newton dynamics at steady state, their leakage is less. So the change in the slow Newton dynamics is considered 0, and leakage of the slow Newton, the thermal neutrons is much smaller. Then that is all are neglected. Then the RH is obtained, and then this RH is substituted in this equation. Then one gets this one group equation, 1.5 group equation, which represents the flux dynamics of the zone. So there are 14 zones. So there are 14 flux equations, or it are obtained, which are represented by ordinary differential equation. Of course, not linear. I will come to the linear part. Then what is done here? These are useful to determine the coupling coefficients, this kind of approximations, macroscopic cross section, and other parameters required in one group, which 1.5. Finally, the one group, the flux and the power are algebraically related, and that flux equation is converted into the power equation like this. So this is the power equation of the zone H, which is represented by again an ordinary differential equation, but of course a nonlinear equation, by using these algebraic relations between the flux and the power of that particular. So similarly for the precursor, it is done, similar variation, the precursor concentration. So finally what we get here, that for H zone, one power equation and one precursor equation with all these that are substituted. So this is for 14 zone, there are 14 power equation and 14 precursor equation, so 28 different equations. Now we have yet to get more equations, more dynamics for the xenon and the ion. So then after that the reactivity is introduced, the one neutron lifetime and infinite multiplication factor, they are related to this. Then the KH, that equation can be represented, this power equation can be, this equation can be represented, that the reactivity has to be introduced here, so that reactivity is related to the multiplication factor, and so what we get here, that dph dt, that dph dt is multiplication factor, and with all these substitutions we get the further simplified equation of the zone H power equation and zone H for MD group of precursor. So if there are 6 groups, there will be 6 of this equation for H, for the H zone. Then here again the reactivity, which is related to the multiplication factor by if K is 1, then is a critical reactor in a global sense, global reactivity, or for a zonal case, and for that zone. So if K is more than 1, it is a supercritical reactor, that is no reaction will take place, then the absorption, and if K is less than 1, it is subcritical reactor. So these are the reactivity, and this is the reactivity which is inside the reactor, that is due to the xenon, that is due to the transmutation of xenon. Xenon absorbs neutron, so it changes the reactivity. So this term is responsible for that. And this reactivity is due to the external reactivity, which is created by the controlling the level of the water of the FCC compartment. So this is the power equation, is the precursor equation. Then we have to look for the xenon equation. And for the xenon equation, we have to consider the dynamics of the iodine. So rate of change of iodine, again for the whole reactor, then we convert into again for the zonal dynamical equation. So this is the, at this rate, the fission takes place, and this is the yield part fission. So at this rate, the iodine is produced, and at this rate, the iodine begins. So this is the dynamics, the rate of change of iodine, and then this is the xenon. At this rate, the directly the xenon is produced, because at this rate, the fission takes place. So this is the yield part fission, and at this rate, from the iodine, the xenon is produced after several hours. So this is changing the dynamics of the xenon, and the xenon itself decays. So this is the decay rate, and this is the curve which I was telling. Xenon absorbs neutron, and it changes the xenon back. So this is the iodine dynamics, this is xenon dynamics, and then when it is written in terms of the every zone, then again it is, the flux and zone, it is converted into ordinary differential equation. So this is the iodine equation for zone H. This is the xenon equation for the zone H. So there are 14 of power, 14 of precursor, 14 of iodine, and 14 of xenon. So 56th order ordinary differential equations are obtained so far. But there is another equation, another 3 equations, 14 equations are to be considered, because the reactivity is a term, mathematical term. You have to control through some means. So the reactivity and the actuator, the GSCC compartment, the level of the water, and the reactivity, I understand that is calculated also obtained at ERC, that the reactivity is, this formula is obtained, that the level of the water and the signal to the valve, one signal which is applied to the valve, and then the water level is controlled, they are related by this. That is also developed by Dr. Tiwari at EFC, and then the reactivity and the level, they are proportional. So they are related by this equation, then this equation and this equation, and then if you write the whole 540 megawatt based nodal approach, then there are 14 power equations, 14 precursor equations. We consider confine our discussion one group of precursor, then 28 and iodine xenon, and there are 14 is actuated. So total there are 5 differential 5 into 14. There are 5 differential equations per zone, and if it is divided in 14 zones. So 5 into 14, the total 70th order differential equation, nonlinear of course. This model represents the whole dynamics of this 540 megawatt with now the controls we have to take. So for that, again, we have to linearize this equation, So linearized operation of the reactor in steady state, total power, the zonal power is the global power is the summation of all the local power, zonal power PA. I want to get zones out. Consider these 14 zones. Bilateral precursors, iodine, xenons are in equilibrium with the zonal power. Then consider an incremental change delta Ty in the world system, and they are linearized with respect to their the incremental power, incremental precursor, incremental iodine, incremental xenon, and incremental then delta H, and then it is linearized, then the linear quantity. So there are in the earlier equations and non-linearity, which is converted by considering an incremental variable over the equilibrium, and the equation is linearized. Then this linearized equation, 70 linear equations are obtained at full power. Then they are normalized. The iodine xenon, they are the slow variable, and slowly the power is the fastest variable. So the whole state vector is written. There are 70 states, and each zone has an incremental that the FCC is disconnected to a valve. So signal in the valve is considered the control. It is that control input has to be designed using a sliding mode in this lecture we are talking. So they are the control input. So there are 14 input signal which is applied to the valve, by which the level of the 14 jet CC is controlled, and by which the flux is controlled, and by which the ultimately the power of. So this is represented, and this is a normalized power of 14 volts, the 14 input of 70 states, which is states in sport. Now the control engineer is familiar with this kind of model, and they can go for the design of control. So this is the task which is done. Now I will be speaking on something on the control. So these are the A, B, C matrices, and the matrices, linearized model for control design, unstable system. There are poles, 14 poles at the origin, very high order. For this is 2 times the property system shifts. Some variables are often in a very less time constant, some are very slow, so slow and fast hits. There is a technique, the whole lot of research has been done similar for this technique, and how to handle such system. That if there is a time scale in the system, different time scale, system is state system, then it can be decomposed into slow system and the fast system. And then a slow controller can be designed and a fast controller can be designed. There is a famous paper by father of nonlinear theory, and then individual controller can be designed and a composite controller can be made, and it has been shown in that famous paper of Prokopyev's that is close to the near optimal control. It is designed a full optimal control system. Advantage is that one can decompose the system and one can design the lower order controller. So these are the problems for this model. After developing the model, it was found system is state time space system could be observed for 10 there are xenon with a large time constant. So the system response after designing the controller could be observed for several hours. To conclude the performance of the controller, then the system is controlled within an observed minutes. Among various control, the sliding mode control, as much has been spoken in this tool from yesterday. The sliding mode control, as I told, was a very simple structure. It doesn't have a big mathematical, expression of the controller like H2, H and P. It is a simple controller with some logic, and that is the advantage very much. That's why the sliding mode control has become very popular, while one of the accepted design techniques for the robust control. As I told you, that it was invented, it is known, the originated in Soviet Union in 1950s, and then it was confined there. Then after a seminal paper of Putin in English language in IIT production, I think in 1977, it sparked research interest on Dr. One. And then, as I told you, the technical committee in IIT Control Systems to conduct any step conference. And France, it was held in 2014. So these are the sliding mode sensing control structure, disturbance rejection, order of the system, reduces building sliding, then the natural order reduction in the first order sliding. Then in theory, the continuous time sliding mode, it completely rejects disturbance. No controller, the match disturbance can be rejected completely. But in sliding mode control, if there is a switching function, then in continuous time it exactly gets, and then the flip of solution when it slides. So that's why, and that is free from the system. That is another very big advantage. So many continuous are available. Discrete also started with the digital computer, with digital implementation. The discrete time computer has become also to be popular and got a place to look into. The discrete controller can be designed. Now again, there are two schools of thought, as I was discussing, that there can be a discretized system, then design a discrete control that you apply to that case. Another is the continuous control. In discrete manner it can be. So there are two ways it can be taught. So discrete time slightly more. Much research has been done. First started by I'll tell you, in 1985, the first paper came in discrete time sliding, discrete concept first came, that how the discrete time sliding can be, what happened. So first approach is obtained by not necessarily in 1985 that the paper, and then of course after that the famous paper came, the Gauss paper, the signum function, the discretization, there is a discrete time reaching law. I think it's still, in 1985, I think Minnesota, isn't it? 1985 paper. Yeah. So first the discrete concept, then after that, a lot of that discretization of the continuous reaching law, the guaranteed finite time reaching and then sliding. So that research result came by the Gauss paper, very famous. I was interested in that, just got several thousand citations. That's very important. It has been shown the direct discretization of continuous reaching law. It does not give exact slide, even without experiments. That is a very deep observation. And it can abound the sliding surface, it can interdict motion and interdict that. Then it has been done a robust of that. Also, that kind of property, but it can increase the band, then without disturbance. And then, of course, large result has been done. One of my former students who is not here, the discrete multi-rate must be proposed. Using the state feedback, the things are all states should be available. But many seldom they are available, so there are output feedback stabilization is not getting. There are many papers, many results. In sliding mode also, it is done by Edwards and Saraswat, under certain condition, the output feedback sliding can be obtained. So in multi-rate, we have shown that if we control within an observable system, then always a given sliding mode, state feedback based, can be converted into an output. And it gives the same behavior as it is obtained by state feedback. Then the quasi, that is some important quasi sliding mode, then Roorkee is that they say that is a quasi, that is not exact sliding. So without switching, they propose the equivalent control. And without disturbance, you can exactly slide. That is the sliding mode for split times, which is again further modified by the Andres, the Kusuri, and researcher in a different dimension. The rate of convergence you can also control. You can go slowly, then the control effort will be less. You can go really fast, control effort much. So one can make a trade-off, how slow or how fast you want to reach the sliding surface. But idea is that non-switch. So these are the concepts. So here, what I am trying to discuss, some implementation of discrete sliding mode, and then some nice simulation, which is done. Then I am discussing Bartholomew, the state feedback, completely eliminate battery, signal function at all, bring the trajectory from initial state to the sliding surface one second. It's first approach, but one can again change that thing. Slowly one can come by applying and scaling the control. One can come directly, the equivalent control is applied, then in one sampling time, it can reach exactly to the sliding surface. Then he has proposed you can scale the control so that different sampling is done, and there is a guarantee that the condition by which it will approach towards sliding surface. So that is the modification. So here I will discuss that. Bring the trajectory one sampling, maintains the trajectory exactly on the sliding surface. Control effort can be planned by ensuring sliding mode control. That is by scaling the control. But it will guarantee to reach the sliding mode. Then quickly I run down the first output sampling based Discrete times like remote control, the continuous, and with the discrete function in the first output sampling idea that was first proposed by Kuroda, our Japanese scientist professor, and Harvard Brain, that using the first sampling, you can realize a different state effect, provided the number of integers is greater than the observability rate of the system. Then whatever you get the closed loop system effect, same effect can be obtained by replacing that state effect by a multi-rate or first output sampling. So this is the delta. There are two sampling times involved. We are not going much details of the theory of this. And then this theory, the discrete system of this reactor, discretized, and this is the new factor. A proposed an observer is proposed by this multi-rate observer or first output sampling observer, that xk can be obtained by, this is the y of subscript, not the argument. So that's the stack of output, fictitious, that is the lifted output. And from that output, in one sampling, the next instant, the state can be observed. What is nothing but the multi-rate observer. So x can be exactly obtained without uncertainty, and if uncertainty is the relations. These are the different matrices. And then this is the written law. We have little modified the principal law. In principle, when state class 1 is 0, but if you consider certain bounds and all these things, these are the uncertainty and these are the variables, then the state class 1, the written law is getting modified. And then, so that it's so modified, the control is free from the uncertainty. So this is the discrete times like remote control for this reactor feature 25. Then this control, much is discussed in our papers and book. I am not going much details, but what is important to show three important simulations. These simulations are, one is the power maneuverability inference, another initial power dispatch, and external dispatch. Each simulation is really shows the performance of this controller. Nonlinear simulation, nonlinear equation, several hours it is done. So first is the power maneuverability, what is done here. The global power is 1800 power. And then in 10 megawatt per second, the demand is changed, new demand. And every 10 megawatt per second, the demand is changed. The global power is changed. And it is changed up to 18 seconds. And after that, it is very constant. So this kind of, the power, if it is changed, the new demand, how it is reaching, how the controller is performing. So there are certain quality things. These are the simulation system that in 3000 seconds, the global power settles to its new demand with an error of 1 plus minus 1. This is one of the reasons. So the new demand, 1620 megawatt from 1800 megawatt, 10 megawatt per second it is changed, and then in 3000 seconds it reaches to the new demand within 1% plus minus 1%. This is one simulation to show the performance of the controller, and then the zonal power settles within 1 plus minus 1% in 450 seconds, and similarly the xenon and iodine, they settle in 15 hours. Because their simulation, that's what has to be carried out for a longer time. Because the whole dynamics, their dynamics is so slow, so one has to observe the simulation for several hours, whether they are stabilized. If they are not stabilized, then it can be a problem for that nuclear reactor. So those are simulation, and also the control. These are the xenon concentration, iodine, they settle in after 15 hours. And the global power and control including 150 seconds, they settle almost to their mean demand, and control also becomes 0. After initially there will be change, but then because it is a change of the demand, and then finally it becomes. So this is one simulation. Then another simulation is the applications, the power maneuverability from 1800 megawatt to 1620. Then there is a tilt, which is a very good term by which the performance of the controller can be judged. One is the axial tilt, power in the one axial hub, another axial hub divided by global power, side to side tilt, and top to bottom tilt. Power in upper hub minus power in lower hub by global power. So there are 3 fields. What is the importance of these fields? That one simulation part has been shown that if the initial values of the zonal power, if it is little changed, in simulation it has been done. If it is little changed, then it's desired value. And then what has been shown, then this controller is applied, the multi-rate output feedback-based controller. Then it has been shown that with this change initial power, this matching the initial power, then the actual desired power. When the global power is the 1800, then there is a desired zonal power equivalent and equality point. So that power, if it is little disturbed and then little change, and then the tilts are kept. So what it is found that in this controller, these tilts are 2% axial mismatch in the initial power. Whereas the desired tilt, desired initial condition, the top to bottom is 2% and no tilt side to side and X. So that means the tilts are under control. That is one half power in one half of the reactor minus another half. So that change, the difference is settling down. So that is a measure how you do your control, the spatial control. So this is one simulation is done. And then another is the zonal power. That time the zonal power variation and also the tilts are shown. That's what I explained. These are the tilts from the desired tilts and the mismatch in initial quantity. Then the third simulation is the global power. That initially there is a change in the global power because it is a different initial condition, but it settles to the new desired power, the actual desired power. It settles. External disturbance. If there is a disturbance, matching disturbance is applied. And the disturbance is in this reactor 0.01 volt per second in the zone 1, some voltage, some signal is added to the input, the control, and then first 10 seconds. And another 10 seconds, this 0.1 voltage per second is decreased, and then it is made 0. So this kind of disturbance, it is created, the match disturbance, because it is added to the input control input. Then what has been shown, the zonal power variations, these are the variation, because initially there is a disturbance, so zonal power will vary, but finally it tends to significant. And the zone 1, zone 8 and zone 14, the construction is such, the zone 1, this disturbance is created, so the changing the control input, the zone 1 is maximum. And then this and the power in the zone 1, changing the zonal power is 3%, zone 8 is 1%, and zone 14 is 0.4%. This is the change in the zonal power due to this disturbance. And similarly, there is a large change in the control input of the first zone, and what all this is effectively they are controlled. So these are the tilts are also initially it will increase due to the disturbance, but it settles to its or its desired. So conclusion is the large reactor is a complex nonlinear system. It is characterized by huge number of state variables. Controlling a nuclear reactor is challenging. A number of approaches have been developed. Focus here is the application of discrete time HLC. It has been shown that the reactor power and core power distribution are effectively controlled in a number of scenarios. Applications of DSMC is somewhat straightforward and free from income. Implementation through estimated states based on first observation is easy, then to cloud with an observer and to estimate the states. So these are the conclusions. Several articles starting from Dr. Tiwari, first researcher on this topic, nuclear science transactions, and then one of the notable things is that, this work was, we were happy that it was invited to publish a world largest online encyclopedia, 400 things for the equivalent to that. So we were invited to contribute an article to that encyclopedia. That is that EO-ended publisher, and this is a publisher, is an encyclopedia. There is a section, 200 articles in that section, control and robotics, and the total volume of the encyclopedia is put. So there we were invited to, and many of the papers are in IIT transactions on nuclear science. So several years the research is going on. Several people have done after Dr. Tiwari. So I am just a, you can say, initiator kind of. I could tell several papers. I am just a. So several people have. I'll show these are the first row. They are all PhD on this year. Different projects. The first row. Starting from Dr. Tiwari. When he started, he was young. Then he retired. He is now visiting professor in one. Then after that, he's another scientist in DRC. They are IIT PhD students. So first row, they did PhD on nuclear. Second row started from discrete time slicing. She has done very good. She is now a full professor, global chair in UK in Lincoln University. And then all have done. The IIT Delhi professor, IIT DHU, IIT near in Ahmedabad, IIT RAM, and Abhishek in IIT Roorkee, Soham is IIT Roorkee. Second and this row, they are all second and third row, all on discrete time slicing. I think what is not done. So this is all about it. I'll be happy. This is all about it. I'll be happy to ask your questions.
Long live India and France friendship.